So in the last lesson we learned how to deal with drag. This lesson is going to deal with lift. It's very similar to drag, other than the fact that drag is horizontal, lift is vertical. But what we do is we have a lift coefficient. So my lift coefficient CL is the force of lift divided by 1/2 rho v squared times area. And generally we're not calculating the lift coefficient, we're finding the lift coefficient through tables or whatever else like we did for drag. Then once we have that lift coefficient, we can find the lift force. FL is 1/2 CL rho v squared times area. So generally when we're dealing with lift, we're dealing with things like wings or airfoils, actual lifting surfaces, things that actually make you fly. And so because of that, I need to know some nomenclature here. So I have a wing or an airfoil. An airfoil is basically a two-dimensional representation of a wing. So if I have a wing that's really long, I can represent that by just 2 dimensions. So I have thickness T, a chord length C, so that's the direction that the wind's going. That direction on the wing's the chord length. And then my wing span B, so how long my wing is. And generally when we do this, we're just dealing with a wing. So when I say wingspan, I mean the entire wing. Generally that's all we're looking at. We don't care about the plane in the middle. So wingspan is the entire wingspan of the plane. Now one other slight difference, lift and drag. When I dealt with drag, usually the area that I wanted was the area that was facing the flow. So in this case, if I wanted drag force, I'd look at area like thickness times wingspan, because that's what this would see if I was looking at it. But for lift, the area that you want is usually the plan area. So my plan area is the chord length times the wingspan. So again, in this case, the perpendicular area to the direction of the force. So drag force going this way, I want the perpendicular area. For lift, force going this way, I want that perpendicular area, so B times C. Now having said that, in the last lesson, as I said, the drag force, we wanted this perpendicular area. We're going to see some drag curves in this as well. So generally we have drag curves for wings. Those are usually given as a plan area. So that's the one situation where you do not want the area we talked about before in the previous lesson for drag. We actually want this plan area for both the lift and drag when we're dealing with wings. So now we want to know how to actually find the value of CL, just like we did for the drag force. We want to find CD in tables and things. So how do we find it, or how do we find CL for a wing or an airfoil? And so my coefficient of lift is going to depend on a couple things. Most important ones is angle of attack, it's the first one. So basically I have a wing, and if my wing is going flat, it's going to have a different angle of attack than if that wing is pitched up. So it's the plane taking off, angle of attack is going to change, and that's going to change how much lift the plane is going to get. And generally, bigger value of alpha is going to give you more lift, but that's only up to a certain point, as we're about to see. Because after a certain point, you start to get boundary layer separation on the back side, and that decreases your overall lift coefficient. It could also lead to something called stall, which we'll talk about in a few minutes. This video shows an airfoil at increasing angles of attack. Eventually you see boundary layer separation on the top side, right there. That's going to increase the pressure on the top side, which decreases the overall lift, decreasing the value of CL. The other significant aspect of the lift coefficient is the shape of the wing. So there's 2 main categories for shape. There's symmetric and cambered. So symmetric airfoils are symmetric, so these guys are not going to produce any lift if you have an angle of attack of 0. So it's just flying straight. Top and bottom is exactly the same. So there's no reason to have any pressure difference top and bottom, so you're not going to produce any lift. As opposed to the cambered airfoil, these guys are shaped, so bottom goes up a little bit. And what that does is it makes the air go over the top faster than the air going under the bottom. So what that does, Bernoulli's equation, lower speed gives higher pressure. So if I have a lower speed on the bottom, I have a higher pressure, higher speed on the top, lower pressure, that's going to generate lift. So even at 0 angle of attack, these guys are going to produce lift. Symmetric airfoils are not. So the situation of stall is generally defined to be a situation where the wings are not producing enough lift, and this can be either due to having a CL that's too small. That could happen if my alpha is too big, as we saw in the video, or it can also be because you're not going fast enough, so V is too low, and that situation leads to a definition of a stall speed. So basically the minimum speed you need to go to produce enough lift. Enough lift is generally defined to be the weight of the plane, because that's generally what you want. If you're not producing enough lift that's equal to the weight of the plane, you're not going to stay in the air very long. So stall speed, 2 times the weight of the plane divided by CL max, density and area. So CL max is the maximum CL you can possibly get. When we see, you're going to be seeing some curves in a little bit, so you can obviously see where the CL max happens for some of those. It's basically the alpha that gives you the biggest lift coefficient. So we're going to see that as you increase alpha, lift gets higher and higher, but then this boundary layer separation happens that we saw, and so it starts to decrease, and so wherever that maximum value is, that's generally what we have. So that's the slowest possible speed you could possibly go and still produce enough lift to keep flying. So anytime you're in a situation where you have stall, it leads to significant reduction in control of the aircraft. So it's hard to turn, it's hard to change elevation. So you generally want to avoid this situation as much as you can. Now there's some situations where you're traveling relatively slow in a plane, that's namely takeoff and landing. You're generally going close to the stall speed, but again, you want to be a little higher than that just to be able to control the aircraft, to be able to turn, do whatever maneuvers you need to do. So generally for takeoff, your takeoff speed is generally 20% higher than the stall speed. Similarly, landing, touchdown, your touchdown speed is generally roughly 15% higher than the stall speed. And again, this is to make sure that you can actually control the aircraft. If you need to turn or do anything else, you still have the ability to do that because you're going a little bit faster than stall speed. So the last thing we want to consider before getting to the actual values of CL for wings and airfoils is if you look at what's actually happening to a wing that's in flight, so a wing that's actually flying. So here's my front view, my wing, so it's coming at us, flying. And because it's flying, I know that it has to generate lift. If it's generating lift, that means that my pressure on the bottom needs to be higher than the pressure on the top. So I just model that with a little plus sign. So plus signs on the bottom, minus signs on the top, so higher pressure on the bottom, that's why this thing's flying. But now if I have a lot of high pressure on the bottom, a lot of low pressure on top, what's the air going to want to do? And so because the air can move, it's going to want to move from this area of high pressure up to this area of low pressure, so it's going to swirl around the tip of the wing on both sides. And these are called wingtip vortices. You can actually see them if you're ever flying in a plane. So look out the window as you're going through clouds and things, you can actually see some of that air swirl around the edge of the wing. Sometimes, depends on what the wing looks like. Now these are actually not good for 2 reasons. One reason is if you look at this, I have this air coming around, and as it's coming around, it's basically pushing down on the top of the wing. If you're pushing down on the top of the wing, that's going to reduce your amount of lift. So one thing that these things do is actually reduce the amount of lift. Another thing that they do is my wing is making this air swirl around. Making air swirl around takes energy. That energy needs to come from somewhere, and that generally comes from the engine of the airplane. So essentially what you're doing is increasing drag, making more or less fuel efficiency. So generally planes don't want these. So the way they generally fix that is to add something called winglets. So little turned up edges of the wings. You probably see those in planes as well. And so what that does is it stops this from happening. So put a big barrier here. It's going to stop the air from actually swirling around. So it's going to stop this effect from happening, which means you're not losing any lift, you're not losing fuel efficiency, which is really good. Now this doesn't actually affect fuel efficiency that much, something like less than 1%. But if your gas bill for these major airlines, billions of dollars a year, 1% of that is a good amount of money. So this leads to the last thing that the coefficient of lift CL depends on, which is something called the aspect ratio, defined to be the wingspan B divided by the wing chord C. So those wingtip vortices only happen at the ends of the wings, at the tips. So if I have really, really long wings, it's only happening way at the very ends, and compared to the entire length of the wing, I can pretty much ignore it. But for shorter wings, this is going to have more of an effect, so that's why this aspect ratio is important. If you have a high value of lambda, the aspect ratio, you're going to have long, skinny wings, so things like gliders, these are the type of wings they have, mainly because it produces a lot of lift, not a lot of drag. So if you're in a glider, that's really good. You don't have an engine to help you out. But on the downside, it's going to cause more stress. So the wings are really long, it's going to cause a lot of bending stress in them. It's also going to have not very much maneuverability. On the other hand, if you have low value for the aspect ratio, all the opposite is true. You have not as much lift, more drag, but more maneuverability, and that's generally what you want in something like a fighter plane. Fighter plane, you have a really powerful engine, so you don't care if you are reducing more drag and less lift. You can compensate for that by just firing up the engine, and you definitely want a lot of maneuverability in that case. So first example, we have an airplane, weight of 10,000 pounds, flying at 30,000 feet. At 30,000 feet, to have a pressure of 3.3 psi absolute, temperature negative 67 degrees Fahrenheit. Way the plane is flying has a lift coefficient of 0.2, has a wing area of 400 square feet. So I want to calculate how fast I need to go for level flight. So level flight means I'm not going up or down, so essentially force of lift equals the weight of the plane. So how fast I need to go to accomplish that. So solution to this, I know my lift force is 1/2 CL A rho v squared. I want that equal to the weight, like I said, to have steady level flight. So we can rearrange this formula to solve for the velocity v to be the square root of 2 times the weight over density, lift coefficient, and area. We know everything in that equation other than the density of the air. However, we do know the temperature and pressure. So with that, we can use the ideal gas law. Density is pressure divided by R times T to find the density. So pressure of 3.3 psi. Want that in PSF, so multiply by 144 square inches per square foot. Then the R value for air, 1,716 foot-pounds per slug degree ranking. And then my temperature, absolute temperature, so 460 minus 67 degrees Fahrenheit gets that into ranking. And that gives me a density of 7.05 times 10 to the negative 4 slugs per cubic feet. Now plug all those numbers into my equation for velocity. So 2 times the weight of 10,000 pounds, density 7.05 times 10 to the negative 4 that we just found. CL was 0.2, and then area of 400 square feet gives a velocity of 595 feet per second, which we can convert that to miles per hour. It's 406, which is a reasonable speed for an airplane, so generally happy with that. So in the next example, we have a light airplane weighing 10 kilonewtons, has symmetric airfoils, total wing area 15 square meters. Want to find the angle of attack. If we want our takeoff speed to be 140 kilometers an hour, assuming standard atmospheric conditions, and 2 people in this plane weighing 800 newtons each. So one of them is obviously going to be the pilot, the other one maybe a co-pilot, but 2 people in addition to the weight of the plane. So at standard atmospheric conditions, STP, we know the density of air is 1.2 kilograms per cubic meter. My velocity, 140 kilometers an hour. I want that in meters per second, so do those conversions. I get 38.9 meters per second. Then the total weight, plane and the 2 people, 10,000 plus 800 twice, is 11,600 newtons. And so from that, I can find the necessary lift coefficient. So my lift coefficient is 2 times the weight divided by rho v squared area. So 2 times that total weight of 11,600 newtons, density 1.2, velocity 38.9, square that, and then my area 15 gives me a lift coefficient of 0.85. So that's what my wings need to be doing to achieve this takeoff speed. Now I know the wings are symmetric, so to find the angle of attack that corresponds to that lift coefficient, I can go to figure 11.13. So answer to this problem, angle of attack, roughly 8 degrees. So follow-up question to this, I want to know what the drag force is in that previous example. So as you're taking off at 140 kilometers an hour at an angle of attack of 8 degrees, what drag force are the wings generating? So to enter this, we need to go back to that same figure, 11.13, because there's also a drag curve associated with that. So we want to find the drag coefficient CD at that angle of 8 degrees. So doing that, we saw a drag coefficient of roughly 0.011 for this scenario, for CD. So now it's just a matter of finding the drag force like we did last lesson. My drag force is 1/2 CD area rho and v squared. So 1/2 times my CD value, 0.011. Then my area, again, this is the area of the planform area of the wings. So those drag curves for the wings are always the same area as the lift curves, so you don't have to go and calculate wing thickness or anything of that nature. You don't have to worry about different areas. So these areas are always the same on those curves. So again, it's 15 square meters. Then density 1.2 and my velocity of 38.9 meters per second gives me a total drag force of 150 newtons in this case. Another follow-up to this question, want to know what the stall speed is in that previous situation, so stall speed for that plane. So stall speed given by the square root of 2 times the weight divided by density, CL max, and area. So based on this, I need to know the maximum lift coefficient that my wing can produce. So I need to go back to that figure, 11.13, for the symmetric airfoil. So we get a CL max value of 1.55 at an angle of attack of roughly 60 degrees from that figure. So plugging that into my stall speed equation, 2 times the weight of 11,600 newtons, density 1.2, CL max 1.55, then the wing area 15 square meters gives a stall speed of 28.8 meters per second, which is 104 kilometers an hour, so just over 60 miles an hour. So I want to make sure you're going at least that fast, otherwise you won't be flying for very long. So last example, we have a plane, has a chord length 2 meters for the wings, aspect ratio of 3, flying at 120 meters per second, angle of attack of 4 degrees, weighs 12,000 newtons. Someone needs to fly this thing, so assuming you weigh 800 newtons, air density for your flight is 0.91 kilograms per cubic meter. I want to know 2 things. First thing is how much cargo can you carry, and second thing is what power engine do you need. So to answer this question, have some preliminary data want to get. For one thing, the wingspan. I know I have a chord length of 2 and an aspect ratio of 3. So the wingspan I can get by just multiplying the chord length by the aspect ratio. So 3 times 2 meters gives me a wingspan of 6 meters. I'll need to know the wing area. Now that I know the wingspan, just wingspan times wing chord, so 6 meters times 2 meters gives me 12 square meters for that. And then last thing I'm going to need are the lift and drag coefficients. So for part A, I'm going to need the lift coefficient. For part B, I'm going to need the drag coefficient. Both of those found in figure 11.16 for this 3-dimensional wing with aspect ratio. So aspect ratio of 3, angle of 4 degrees from the figure gives me CL of 0.55 and CD of 0.012. So now that we have those numbers, we can actually solve the 2 parts of the equation, or the question. So part A, we want to find the cargo load. To do that, we can find the lift force, and then whatever the total lift force is, we can subtract away the weight of the plane, weight of the pilot, and whatever's left over can be used for cargo. So total lift force, 1/2 CL area rho v squared. So 1/2, 0.55, 12 square meters, 0.91 kilograms per cubic meter, and my velocity of 120 meters per second gives a total lift force of 43,200 newtons. And then take away the weight of the plane, 12,000 newtons, weight of the pilot, 800 newtons. What we're left over is 30,400 newtons, and that's what a total cargo load we can carry. And then the second part, the power. So your power is force times velocity. That's force in the direction of the velocity. So my velocity is horizontal. So I want the force to be the drag force. So I need to find the drag force first. So very similar to the lift force, my drag force is 1/2 CD area rho v squared. So basically the same equation, other than now I have my CD value, 0.012, instead of the CL value, giving me a drag force of 943 newtons. And as I said, the power, take that drag force multiplied by the velocity, so 943 newtons times my speed of 120 meters per second gives a total power required of 113,000 watts or 113 kilowatts.